Right, I'm looking at the integral from 0 to 1 of x cubed, and I want to estimate that integral using 4 rectangles with right endpoints. So I'm looking for R4. Okay, so it always helps to draw a picture what you're looking at. So x cubed looks something like that, but I'm only interested in 0 to 1 area under the curve, and I'm going to use 4 rectangles, so break this into 4 pieces. So I've got 0.25, 0.5, 0.75, and I want to use right endpoints to make my rectangles. So I've got this rectangle, this rectangle, this rectangle, and this rectangle. So I want to add up those areas. So each rectangle has a width of 0.25. So I'm just going to pull that right out, 0.25. And then the height of the rectangles, my first rectangle, its height is 0.25 cubed, because that's how I get the function value, by plugging 0.25 into the function x cubed. Okay, and then my next function value that gives me a height of a rectangle is 0.5 cubed. And my next one's 0.75 cubed. And the last rectangle has a height of 1 cubed. Okay, so that's just a plug into the calculator kind of thing, and we get 0.390625. All right, and if I wanted to use 8 rectangles instead of 4, I'll just put in another color my 8 rectangles. So I'm going to break this into 8 pieces instead of 4, and build a rectangle on each one. That's going to give me a more accurate estimate of the area under this curve than 4 rectangles did. More rectangles is always a better estimate. So this time, the width of each rectangle is 1/8. And then the height of my rectangles is the height of the function at the right endpoint of each interval. So I'm going to have 1/8 cubed, 0.125 cubed, plus 0.25 cubed, plus my next one, blah, 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 up to 1 cubed. And that comes out to 0.31640625. All right, this last part is asking you to calculate the exact value using a limit of Riemann sums, not the fundamental theorem of calculus. So that means I'm going to let the number of rectangles go to infinity. So I just did 4, then I doubled it and did 8, and I got a more accurate answer. So I'm just going to let that n value, the number of rectangles, go to infinity. So this is not something we've done in class. It's not something that would show up on a test unless it was maybe some kind of a bonus question. So feel free to stop watching this video now if you're not interested in how to do this. Okay, so my integral from 0 to 1 of x cubed, it is going to be r sub n, the right-hand Riemann sum with n rectangles, would be 1 over n is going to be the width of every rectangle, because the entire interval has length 1, and I'm going to break it into n equal pieces. Okay, and then my first rectangle is going to have a height of 1 over n cubed. My next rectangle would have a height of 2 over n cubed, then 3 over n cubed, until I get to n over n, or 1 cubed. Okay, so now I'm going to rewrite this using summation notation. So keep my 1 over n. And then all of these terms look the same, except for the numerators are changing by 1 every time. So I can use summation notation to write this as I over n cubed, where I starts at 1 and goes up until n. It increases by 1 every time until it gets to n. All right, so a little bit of algebraic manipulation here, and I have the sum as I goes from 1 to n of I cubed over n cubed. Just cube the top and bottom of that fraction. All right, and then n cubed is just a constant. So I'm going to pull that right outside of my summation. So I now have 1 over n to the 4th times the sum from I equals 1 to n of I cubed. And now, this is why I told you in the hint a special formula for how to add up the first n integers cubed. So you have a formula for calculating the sum from 1 to n of I cubed. All right, I'm going to jump to a new slide here. I'll rewrite what I had there. I had 1 over n to the 4th times the sum from I equals 1 to n of I cubed. Okay, so now I replace that summation with a formula. Okay, so that formula is, I still have my 1 over n to the 4th, that's staying, and then my formula is n times n plus 1 over 2 all squared. So I'm going to do some algebraic manipulation here, and I have to square every single piece of this fraction. So I square the n and I get n squared. I square n plus 1 and I get n squared plus 2n plus 1 all over 2 squared, which is 4. All right, I can do a little canceling here. That n squared cancels with my 4th and becomes a squared. And then I'm going to bring my 1 over n squared, multiply these two fractions together. So I've got n squared plus 2n plus 1 over 4n squared. I can break this up into 3 fractions. N squared over 4n squared plus 2n over 4n squared plus 1 over 4n squared. All right, this is how you calculate R sub n. That is the right-hand Riemann sum for an arbitrary number of n rectangles. If I want to get the integral from 0 to 1 of x cubed dx, that is equal to the limit as n goes to infinity of R sub n, which would be the limit as n goes to infinity of n squared over 4n squared plus 2n over 4n squared plus 1 over 4n squared. Okay, so now I just have to think about these limits. In my first fraction, the n squareds cancel, so my limit's going to be a 1/4. In my second fraction, this n cancels with one of these n's, and so as n goes to infinity, that denominator is going to blow up, and the whole fraction will go to 0. And then the same thing happens in the third fraction. The denominator is going to blow up. As the denominator of a fraction gets bigger, the value of the entire fraction gets closer to 0. So my limit is 1/4.